evening, everyone. My name is Erin McNeil, and I'm here to welcome you tonight to our Institute of Physics Prestige Talk on behalf of the Yorkshire branch. We're here tonight with Professor Chris Lintott, and he'll be talking to us about Weird Worlds, the new science of exoplanets. We also have a few people joining us tonight as well. We have Anna, who you can see here, who will be providing British Sign Language interpretation. We also have Bethany behind the scenes, who's our branch support coordinator, who's helped to organize this evening's talk. So we say, welcome to you all. Thanks so much for joining us. Now, this is a Zoom webinar, so your audio and video won't be visible to anyone else. So there's no way that you can accidentally appear on screen. If you have a question, just type it in the Q&A box. We're going to try to get to them all at the end of the talk. I'd like to do a little test now, though, just to make sure that it's working. So open up the Q&A box, tell us who you are and where you're joining us from. We'd love to hear from you and to see who is in our audience tonight. If you're following us on Twitter, please tag the Institute of Physics using @PhysicsNews, just to let us know that you're there. I'd like to say hey to Paul from Epsom, John from Worksop, Tara from Southeast London, who's in our audience. We have Rosemary as well. It's great to see you guys all joining us tonight. I'd also like to mention that this lecture is being recorded and it's going to be uploaded to our IOP Region and Nations YouTube channel so you can enjoy it in the future. Now, on to our speaker. We have Professor Chris Lintott. He's a Professor of Astrophysics at the University of Oxford, but I think we know him best on our TVs as a presenter on BBC's Sky at Night. Chris has a new book out called The Crowd in the Cosmos, and if you want to learn more about him and his research, or maybe interact with him online, give him a follow on Twitter. His handle is @ChrisLintott. So we're going to get started with his lecture now, because I understand there is a Mars landing tonight that we don't really want to miss. So again, if you have any questions, please put them into the Q&A box. I can see people coming in. Sam and Maddie from Cardiff, Roger and Diane from Kimberley. Hello, everyone. Glad that you're here. I will now ask Chris to turn his video on, which I believe it is, and go ahead and share his screen. I'm going to spotlight him, and I'll see you guys at the end of the lecture.
Right, hello everyone. Sorry about that. It turns out that you have to do things in a specific order, rather like trying to land on Mars, more about which in a second. I'm very pleased to be here as a guest of the IOP. Thank you very much for spending some of your Thursday evening with me. I want to take probably about 40 minutes to tell you about what I think is the most exciting area of astronomy and possibly the most exciting area in science, certainly one of the most fast moving, which is the discovery of thousands of planets scattered throughout our Milky Way galaxy, which are changing the way that we look at the universe and changing the way that we think about our own solar system. And I use the word look really deliberately there. I think sometimes it's very easy to give the impression that astrophysics is a complicated or difficult subject. People often, when I tell them that I'm an astronomer, say, well, you must be very clever, which is sort of gratifying, but also a bit disturbing, because as astronomers, what we essentially do is look. And sometimes just by looking at the universe, you can get tremendous insight. So take this image. This is a terrible image of a sunset. The sun's just gone down. You've got the twilight sky, and hopefully you can see there about a third of the way across, there's an evening star in the sky. But if we look more closely, you can see it's actually a double star. That's the zoom in there. And that may give you a clue that this is not a normal scene, or at least it's not normal for us. This is the night sky, or the twilight sky as seen from the surface of Mars, taken by NASA's Curiosity rover 7 years ago now, 80 minutes after sunset. And that dot in the night sky is in fact the planet Earth, and it's a double because we've got the Earth and the Moon. And so by looking, we've learned something, but we've also gained cosmic perspective. And I think by looking at solar systems other than our own, we learn about our solar system. And by looking at our solar system, we learn about the rest of the universe. In the same way that by looking at Earth from Mars, we learn about Earth. And by sending craft to Mars, we learn about our planet as well. So hopefully you all know that we're now about an hour and 45 minutes away from hopefully this happening. NASA's Perseverance lander is due to touch down via this slightly complicated and definitely scary sky crane technology on the surface of Mars in a place that's thought to have been once upon a time a river delta, the place where a river flows into the sea. And it's going there because it's thought that's a place where the rocks contain a history of the past. We'll learn a lot about the geology of Mars from this site, but also because this is a place where either ancient life is thought to have flourished or have had the chance to flourish, or where evidence of such life might be preserved. So we go to Mars to learn about its history and to learn about life and the prospects for life out in the universe. I particularly like, I'm currently completely obsessed with the Perseverance mission. I like the fact in particular that it has a very special rock on board. This is a piece of a rock that's in the collection of the Natural History Museum in London. And this is a Martian meteorite, so a bit of Mars that was blasted off, traveled through space, happened to fall onto the Earth, was collected and studied, and they're sending a tiny piece of it back to Mars, a homecoming, if you will, on the rover as a calibration target. So I quite like the fact that we're sending something back to Mars. But mostly, I want to look beyond the solar system. So this is a completely gratuitous shot of the night sky, and I wonder what you can see when we look at it. You can see stars, of course, but there's also gas here, the wispy bits, and that gas is the raw material from which other stars can be made. And if you look at it a bit closer or a bit longer, you can see there's this sort of dark patch about a third of the way across the image from left to right. That dark patch is a place where there's a dust cloud. And to astronomers, we don't mean sort of dust as in stuff that builds up on bookcases. Dust to an astronomer are particles of silicon or carbon. Think sand grains, but about a tenth of the size. Anyway, this dust cloud is actually blocking out light from distant stars. So that's why you see it's a dark patch. And from dust, just as from gas we make stars, from this dust, we can make planets. And so we've got the whole history of planet formation in this single image. But also, I think how we look at images like this, how you experience the night sky when you go outside and look up and see the bright stars that can be seen even from the middle of a city, I think you should think differently about that view now, differently than we would have done just 4 or 5 years ago, because we now know that most of the stars in this image, most of the stars you can see in the night sky, probably have planets going around them. I can even, well, I guess before I get to that, if for a particular kind of scientist, particular kind of thinker, maybe that's not surprising, because you might argue that the physics and the chemistry that form the planets here in our solar system, that's the same physics and chemistry that we know exists throughout the galaxy. And so the processes that happened here, it's not surprising that they happened everywhere else, except that we didn't know for sure. And it's still this profound moment in human history to know that every one of these stars has a system of worlds around it that we could think about visiting or exploring or understanding to tell us new stories about how planets work. I can even show you some of these planets. So this is an image of the star HR 8799, or rather it's exactly the opposite of that. This is an image of the star HR 8799, where the astronomers responsible have done everything they can to remove the light from the star. So that yellow thing in the center, that's not the star, that's just to show you where the center is. But these blobs round the edge are real. Those are 4 planets in this system, which is 130 light years away from us in the constellation of Pegasus. And these planets orbit their star on orbits that take between 45 and 460 years to complete. And they're sort of, the smallest of them is 2 or 3 times the size of Neptune. The biggest of them is 2 or 3 times the size of Jupiter. So this is sort of like a expanded, blown up version of our solar system. And we get to watch them move. So this is real data from the European Southern Observatory's Very Large Telescope. And what you're seeing here is something that you've seen an animation of hundreds of times. So you've seen the animation of planets going around their stars, our planets going around our sun. Well, this is the real thing. We get to watch solar systems in motion. But most of the planets that we now know about, we can't find in this way. I can't show you pictures of these planets. There's not going to be a talk with an enormous number of pretty pictures because, actually not because the planets are too faint, but because the star is too bright and the glare of the star in most cases prevents us playing this trick and getting rid of the light from the star. Rather like trying to see a glowworm flying in front of a stadium floodlight from a distance of a few miles. So what we do instead is we think of new ways of looking, new ways to try and infer the presence of planets. And they're not complicated. Here's an example. The yellow thing here is the sun. You'll remember the sun from, June. But this is the sun on a particular day in 2012 when Venus happened to pass in front of the sun as seen from Earth. So this is a video that was taken in the university parks just outside my office here in Oxford. And this is an event that, because of the way Earth's orbit works and the way that Venus's orbit works, this is an event that only happens twice a century at most. You can see it's rather pretty, but on the right is the really beautiful thing. Physicists like me love graphs. So I think the graph is the beautiful thing here. And all this is a graph that shows the brightness of the sun against time during this transit. And what you can see is that when Venus is in front of the sun appears slightly dimmer. It's not the most complicated measurement. I told you it was simple. When something is in front of the sun appears slightly dimmer, in this case by about 0.1%. But if you watched carefully enough and for long enough, and you were in the right place in the galaxy so that every time Venus completed an orbit, it got in front of the sun from your perspective, then you'd see a regular pattern of blinks. And from that regular pattern of blinks, you could deduce that Venus existed. You could work out its year, its period, how long it takes to go around the sun. And you maybe could start to work out things about Venus itself. You could work out the size of the planet based on how long it takes to go from maximum light to the bottom of the eclipse. And we think there are places in the universe where you'd be able to do that experiment. In fact, the nearest one, this is an artist's impression of a star called Teegarden star. This is a small and hitherto obscure red dwarf, about a tenth of the mass of the sun. It's fairly nearby, it's 12 light years away, and it's known to have 2 planets going around it, 2 almost Earth mass planets, one of which goes around every 5 days, one of which goes around every 11 and a bit days. But the fun thing about those planets is that their orbits line up such that if they look at the sun, all the planets of the sun of our solar system cross in front of the sun every time they orbit. So if you were an astronomer on Teegarden C, the outermost planet, then once a year, you'd see a blip in the brightness of the sun because of the passage of the Earth in front of the sun. So astronomers there would have a fighting chance of discovering the Earth if they could pick out this signal, these faint blips from the data, because this is a difficult measurement. Stars vary in brightness all the time. They get star spots, they pulsate, their nuclear reactions change, and they are slightly unstable. So stars change in brightness all the time. We need to make very precise measurements. And it turns out it's a difficult task to pick out these small blips from the background noise, essentially. And it's such a difficult task that algorithms, computers, aren't up to the job in all cases. And so what we've resorted to doing is asking for help from people to sort through the data. So my team in Oxford, particularly Nora Eisner, who's pictured here, run a project called Planet Hunters, and you can go to planethunters.org now, which will give you some data from a NASA satellite called TESS, T-E-S-S. And we'll invite you to look at graphs for fun, but to look for these dips that signify the presence of planets. And using the system, we're finding all sorts of unusual systems. So my favorite Planet Hunters discovery, for example, is the K2138 system. All exoplanet systems have terrible names. We're not very good at naming these things yet. But K2138 is a system that when we found it, had 5, or when the volunteers on the Planet Hunters website found it, had 5 planets, B, C, D, E, and F. Luckily, they're arranged in that order. And what's exciting about these planets is that there's a pattern to their orbits. So B goes round its star once every 2 1/3 days. But C, for every 3 orbits B completes, C completes precisely 2 orbits. And for every 3 orbits C completes, D completes precisely 2 orbits. And for every 3 orbits D completes, E completes about 2 orbits. And for every 3 orbits E completes, F completes 2 orbits. So there's this 3 to 2, 3 to 2, 3 to 2 pattern that links these planets together. It's what's called a resonant chain that tells us that these planets formed together and they've evolved together. It's kind of a fascinating thing. We've actually even found a 6th planet, which almost but doesn't quite fit the pattern. So if for every 3 times E goes around, F goes around twice. For every 3 times F goes around, well, there should be another planet there, but we don't see anything. But imagine there is. For every 3 times that goes around, there should be another planet. We don't see that one. But for every 3 times that putative planet completes an orbit, G, which we now know exists, and we have observed transiting the star, goes around twice. And the fun thing about this is it almost but doesn't quite fit the pattern. And so it's a nearly resonant system, like a mistuned piano or something like that, mistuned key on the piano, I guess. And it's quite difficult to explain why that might be. We think there might be missing planets in the system. And if so, we're hoping to find them with a European Space Agency satellite called CHAOPS, which is up there now observing known planets, trying to refine their properties by looking at how they interact with each other. So K2138, the single system that was found by volunteers on our website, missed by professional astronomers, has become a playground for trying to understand exoplanets. Now, it'll become important in a little bit. So I should say that though most planets that we know about have been found by this transit, by this blip method. And you can sort of see why that might be. The nice thing about this method is that it's pretty cheap in the sense that I can look at many stars at once. So I can just monitor a patch of sky. The NASA satellite Kepler for 3 years stared at one patch of sky and monitored the brightness of 150,000 stars at once, looking for these dips. So that means that I can sort of hedge my bets. And even though it's unlikely that any particular star will have a planetary system lined up just so that we see these transits, if you watch enough stars, the odds quickly tilt in your favor. But there are other ways we can find planets. Probably the second most important is a technique called radial velocity. And this uses the basics of gravity. So in yellow here is a star, and it's being orbited by a planet in blue. And the important thing to note is that when 2 bodies orbit each other, they orbit their common center of mass. So they don't orbit, it's not that the sun stays static and Jupiter and the rest of the planets whiz around it. The sun wobbles too, and that's what's being shown in an exaggerated fashion in this diagram. And so the graph on the right is the apparent speed of the sun as observed by somebody in the plane of the system. And what that does is, because as something accelerates and decelerates, you get this change in the spectral lines. The spectrum moves by something called the Doppler effect. It goes to red and then blue and then red and then blue. If you watch very carefully the spectrum of a star, then you can detect the wobble induced by a planet. And we can now do this pretty routinely. The precision of this astounds me. If you look at the axis of that graph is ms, which is meters per second. And so we have to measure how fast a star is moving to a precision of less than meters per second, actually getting down to centimeters or tens of centimeters per second. And when you do that, you can pick out the wobbles due to planets and find planets that way. It has the advantage that you don't need the planets to be in line. So this has been used for many, particularly nearby stars, where it's worth putting in the effort of staring at the same star again and again and again. And this is a gratuitous animation of what it might be like to be on a planet called Proxima Centauri b, a planet around our nearest star, which is a little bit, 20% more massive than the Earth, and orbits this faint star every 11 and a bit days. So there are other techniques as well, but together the exoplanet community is making great strides. And in one single week in January, I picked the week randomly, we found HD 1808236BCDNE, so that's a 4-planet system. I did tell you the names were terrible. We found TOI 564b, TOI 905b, and TOI 451b, C, and D. And all of those were found by NASA's TESS satellite. So that's the mission that provides the data for planet hunters. And then the last one is HD 108236F, which is the 6th planet in the system, being followed up by that Chaos probe. But that's 1 week, 9 new planets. 20 years ago, finding a planet would have won you a Nobel Prize. Actually, a little more than that. The first ones were found in 95 and 96. But nonetheless, we've now got to the point where you can find a planet with your web browser, and in a week, it's kind of commonplace to add 9 to the list. So now we've got about just over 4,000 known exoplanets. And this is the up-to-date data from just a couple of weeks ago. So this is the diagram we're going to be spending a lot of time with this evening. And I'm sorry that you've tuned in for an evening of astronomical entertainment where you might have been expecting beautiful imagery. And you've got a blob of a sunset on Mars, and now we're looking at graphs. But stick with me, because this is an important graph. Every dot here is a planet. The colors just tell you how it was discovered. You can see the methods we've been talking about, the green transits, the red radial velocity is this wobble method, and there are a few others as well. The higher you are on this graph, the more massive you are as a planet. The lower you are, the smaller you are. So Jupiter would live most of the way towards the top here. The Earth's in the middle, and then smaller planets further down. The further to the right you go, and then on the bottom is your period, the length of your year. So the further to the right you go, then the longer your period. So the Earth, of course, has a period of 365.25 days. So we sit sort of between the green and red regimes here. And so we can use this diagram to work out what kind of planets we have. And I'm just going to make life simpler. I'm just going to zoom in on the planets that have been detected by this transit method by Kepler, which is this NASA mission that stared at one patch of sky for 3 years. Here they all are. You can see it's still the same thing. So we've got size and we've got period on there. And in the large circles are Mercury, Venus, Earth, and Mars. And so the first thing to note is that we're not really finding planets that look like the smaller planets in our solar system, but that's okay. We understand that. This is a bias. Earth, as I said, obviously takes a year to go around the sun, but that means if you're an astronomer looking for a blip, a transit from Earth, you have to wait a year to get even one. And so we need longer lived surveys that take more time than the 3 years that Kepler spent to be able to detect Earth-like planets in this way. So don't be too put off by the fact that there's a lack down here, but we can sort of label regions on this diagram. So here we are. Now, I'm just going to take us through some of these regions. So the first planets to be discovered, I think, to the surprise of many astronomers, live up in the top left here. So these are the hot Jupiters. So these are large planets, 10 times the size of Earth or something like that, which in our solar system makes you a cold gas giant. But look where they are on the graph. They go round their star in a week, 10 days, even less than that. And so hence the name, hot Jupiter. Some of them are really quite extreme. This is an artist's impression of a planet called HD 209458b, which is just 4 million miles from its star. And it's so close that it could well be described better as a giant comet because its atmosphere is boiling away. And in 1 billion years' time, this planet will have evaporated almost entirely because it's so close to its star. And so that raises the interesting question of how this planet got there. And actually, that's a question that's exaggerated when you think about our own solar system. So here is an official NASA graphic of our solar system that I keep meaning to replace, because if that's the sun on the left, I don't know where the light that's lighting the planets is coming from, but never mind. All I wanted to show you on this diagram is that our solar system has a beautiful pattern to it. There's Mercury, Venus, Earth, and Mars, and then there's Jupiter, Saturn, Uranus, and Neptune. The four innermost planets are rocky planets, and then the gaseous planets are further out. This pattern had been noticed hundreds of years ago, and we thought we had a pretty good explanation for it, which is a shame because it's ruined by the fact that we've now found these hot Jupiters. But let me tell you what the explanation was, and we can pretend that it's still a good thing. So the explanation comes from understanding how stars and planets form. So we know how stars form. This is a place where that happens. This is a shot of the nearby stellar nursery, the Orion Nebula, which if it's clear where you are, you can go outside, look up and see at this time of year. But this is a cloud of gas where the gas is collapsing to form new stars. And it's the light from the newest stars that light up the nebula and let us see the gas. Now, a lot of work's been done to understand the three-dimensional structure of the nebula. And so this is a reconstruction, but this is what we think it would be like to fly in the nebula with suitable cameras. But can you see there are little tadpole-like shapes? Those are protostars with newly forming stars with material around them that's being shaped by the environment of the nebula that they're in. And if we go closer to them, you can see that within those blobs, we're now pretty sure there are disks of material. So you end up with a round star and then a disk of material, which there you go. If we take away the gas cloud, you can see there are jets coming out because the star is active and unstable. But it's in this disk of material that planets are able to form. Towards the end, I'll talk a bit about what we don't know, but I quite like this analogy for what happens. This is a bowl of water will be playing the role of the disk. The disk is rotating, so we're just inducing an artificial rotation here. And we'll just sprinkle in some pepper. You can't really see the grains to begin with, but over the course of a few seconds, the pepper becomes much more obvious. And what's happened is that the grains have started to stick together as they've randomly collided with each other in the spinning disk. And we think the same thing happens in the protoplanetary disk. Grains of dust, these silicon and carbon grains, stick together, partly because they're icy, and form larger and larger clumps. And those clumps go on to form planets, which then shape the disk. This is an image from the submillimeter, so shortwave radio telescope, ALMA, in Chile, of a disk around a newly forming star. And those gaps that you can see, those are believed to be gaps in the disk where Jupiter-sized planets are forming. And once you form a Jupiter-sized planet, it hoovers up everything at the same distance from the star, and you get a gap in the disk. So we're beginning to be able to watch the planet formation process happen. So how does that explain our pattern? We're trying to explain Mercury, Venus, Earth, Mars, rocky, inner, Jupiter, Saturn, Uranus, Neptune, gaseous, further out. Well, in the inner part of that disk, the young star does quite a good job of heating the material. So any gas that's there, particularly any hydrogen that's there, and most of the gas in these systems is hydrogen, will boil away. And so in the inner part of the system, you form an Earth-sized thing or a Mars-sized thing, and that's it. You've used up your material. There's not much else to do. Further out, the disk is cold, and if you form a Mars-sized thing, it will quickly accrete a Jupiter-sized envelope of hydrogen gas. So in the middle of Jupiter, there may be the remnants, the crushed remnants of a Mars-sized protoplanet surrounded by this enormous atmosphere. And that only works in the cold part of the disk. And so what that tells us for these hot Jupiters is that they must have formed out in the outer solar system and migrated inwards. And one of the great lessons that we've learned from exoplanets is that particularly when they're young, solar systems aren't stable. Things can move around and planets can migrate through the disk. In fact, you might turn the question the other way around and ask why Jupiter and Saturn in our system haven't migrated inwards. That's an open problem. We don't understand why they stayed where they were. It's It's probably good news for the Earth that they did. It may be because there were two of them. We don't yet understand how pairs of planets work like this. But we can go elsewhere in the diagram. We go to the bottom left. Some of my favorite planets are the lava worlds. So these are, well, I was going to say rocky planets. They're not gas giants, but they're rocky, but they're so close to their star that they may have melted. So this is a planet called Corot 7b. It's around a sun-like star. It weighs about 5 times the size of the Earth. It's about twice the size. And it's 1.5 million miles from its star. So it's probably got a lava surface. And it's possible that planets like this might be the cause of planets like this. This is the one that was evaporating. If you take a Mars-sized body, have it form in the outer solar system, have it accrete its atmosphere, have that planet move in, and then boil the atmosphere away, you may go back to having a very hot and disgruntled rocky body, which is kind of nicely circular. We may be seeing a life cycle for these planets. But in looking at the extremes, in looking at the hot planets, we may be missing the story here. So it turns out that the most common type of planet in the solar system, sorry, in the Milky Way, isn't a Jupiter-sized planet, but nor is it an Earth-sized planet. It's sort of in between. And one of the lessons, and yes, this is another graph, from these big surveys, is that small planets are common, right? So Earth-sized planets are common, but planets 1.5, 2, maybe even 3 times the size of Earth are the most common of all. This led to fun headlines like, you can't throw a rock in the Milky Way without hitting an Earth-like planet, which is true. You can't. By the way, I'm slightly worried that you're now seeing my presenter view. Could somebody unmute and tell me that if that's the case? Otherwise, I'm just going to keep going and assume it is the case. Cool. Okay. I will just try and reset that. If it doesn't work, we can live with that. I've managed to swap around which screen is which I did by pressing the wrong button. So, by the way, this is why I'm a theoretical astronomer rather than somebody who builds Mars rovers for a living. Hang on, let me just try and fix this. Honestly. Right, is that any better?
Yep. Yeah, looks great.
Sorry about that. Anyway, I was about to make a joke, so I've stumped on my own joke, which is the headlines say you can't throw a rock in the Milky Way without hitting an Earth-like planet, and that's true. I have tried it. But we can go into more detail, because that would have been the story a few years ago, but now we've got more planets. We're beginning to see detail in these populations. And so it's not true that small planets are common. It's that 2 types of small planets are common. You can think of them as super Earths, those slightly bigger than the Earth, and puny Neptunes, or tiny Neptunes. Sub-Neptunes is the formal phrase. And there's a gap in between, and that's real. It's not that we're missing those planets, it's that they don't exist. And so you can think of this, instead of the traditional solar system hierarchy of looking at super Earths and, looking at rocky planets and giant planets, we can now sort of have a family tree descended from the protoplanetary disk where we form giant planets, or we form super Earths, or we form mini Neptunes. We'd like to explain why you have to be one thing or the other. And we think we understand what's going on. We've got this process by which your dust grains clump together. That forms a rocky core, like a Mars-sized core maybe. And then once you get to that size, your gravity is sufficient that you can start growing an atmosphere. But this is a race against time. You're trying to accrete as much gas as possible from your surroundings, but the star is heating up and it's boiling that gas away. So the question is whether you manage to get enough atmosphere to have enough mass to hang on to your atmosphere before the star really evaporates things away. So if you pass that test, you become a mini Neptune. And if you don't, you lose your atmosphere, you go back to being a rocky planet. So it's a very simple idea, just adding this idea that there's this race against time. But it's something that we would never have learned by looking at our solar system, because it happens to be that we don't have any of the most common planet in the solar type of planet in the Milky Way in our solar system, unless there's one hiding on the outskirts, which you can ask me about in the questions if you like. So this is a good example of how we're learning things by looking at the different kinds of planet that we see around us. But it is inevitable that people want to talk about planets and homes for life. Because we do want to look out at the cosmos and know not just that there are wonderful and weird planets out there, but we want to look out at the cosmos and learn about planets like our own. And we will do that. It may have to wait for new technology. We are beginning to find Earth-sized planets, but to understand them and to determine whether they're really like the Earth, we need new technology. The James Webb Space Telescope, which will launch later this year, should help. But I'm particularly excited about this thing. This is a schematic of the European Extremely Large Telescope. We had the Very Large Telescope. We're now building the Extremely Large Telescope. The next one will be the Overwhelmingly Large Telescope. But the Extremely Large Telescope is this beast. The mirror is 39 meters across. You could just see to the bottom right there, there's a car and a couple of astronomers for scale. And the thing that, and that's St. Stephen's Tower with Big Ben in it from London for scale. But the thing that really brought home to me what size this thing was the realization that that's not an observatory dome. That's a sports stadium with an opening and closing roof that happens to have a telescope in it. And this is going to be a marvelous and amazing thing. And it's going to be able to look and help us study the atmospheres of nearby planets. And it's possible that within a decade, we'll be able to point at a star in the sky and say that has a planet that's Earth size and Earth mass, which has an atmosphere which contains within it the signs that there might be life there. You might see abundant oxygen or something like that. That's a real scientific experiment that we can do right now. And if we find that such planets are common, well, then the question about whether there really is life out there begins to gain clarity and focus. And there are already efforts underway. So this is the Parkes Radio Telescope, the DISH as it's known. And Parkes is one of two telescopes in the world that's conducting a survey under the aegis of a project called Breakthrough Listen, that's doing SETI, that's listening for signals from outer space. And they're particularly targeting planets where there may, or systems where there may be planets where our kind of life could exist. And the way that's quantified is usually something called the habitable zone, or more romantically, the Goldilocks zone, which is the region around a star where usually defined as where liquid water could exist. So one good example is there's a nearby system called TRAPPIST-1. It's named after the type of beer. It's a Belgian experiment, discovered it, so that's rather fun. And TRAPPIST is a system of 7 planets, very closely packed, a bit like K2138 that I talked about earlier. And 1D, 1E, and 1F, the 3rd, 4th, and 5th planets of the 7-planet system, might be habitable. They're about the right distance from the star that they get about the same amount of starlight from the star. And if they are, and you go there, this is NASA's idea of what a poster would look, a tourist poster would look like. The other planets would hang large in the sky. And it's fun to think about these things. But I think to answer the question about whether there are really amongst the 4,000 planets that we know of and the others that we infer the presence of, I think to answer the question of whether we really do have homes for life, we need to be a bit more scientific. And I'm a big fan of an idea introduced by Jesse Christensen, my wonderful colleague from Caltech, promoted by Elizabeth Tasker, who's a British astronomer who's ended up at JAXA, the Japanese space agency. So they've talked about the Ecclewatts zone. Never mind the habitable zone. The Ecclewatts zone is the zone where if you picked up Earth and dropped it into that point around a star, Earth would continue to have liquid water on its surface. Because actually the temperature of a planet's surface depends on its atmosphere and composition and all the rest of it, as well as on the star. So if you're in the Ecclewatts zone, you know that a truly Earth-like planet could have existed. And I decided Ecclewatts was clearly an obscure river god. Now, the good news is that Jessie and many of her co-workers have been working hard on this. And this is a technical graph that's mostly there to distract you, but ignore the graph. Half of sun-like stars in the Milky Way have a rocky planet in their Ecclewatts zone. So if you picked a random sun-like star in the galaxy, you ignored all the other stars, there's a 50-50 chance, actually somewhere between 40 and 60% chance, but a 50-50 chance that it would have a rocky planet in this zone where Earth could have liquid water and thus the conditions for life. So that means there are at least 5 billion Earth-like planets in our galaxy, several of which we might be able to follow up with future telescopes. And that likely underestimates the number of homes for life, because if you think about our solar system, yes, Earth is habitable. Mars, as we talked about at the beginning, may or may not have been habitable in the past. But the most promising homes for life in our galaxy are places like this. This is the Saturn's moon Enceladus, which is an icy crust with an ocean underneath it. And the big moons of Jupiter, Europa and Ganymede, and perhaps Callisto, also have these inner oceans. So these watery oceans are way outside the habitable zone in the Equator zone. They're out in the outer solar system, and yet they're excellent places for life. We hope one day we'll explore them. And so that 5 billion possible homes for life is a underestimate as to the number of places where we might look. And so one of the things that our continual discovery of the wild variety of exoplanets is doing is it's really filling in the idea that the potential for life in the cosmos is really great. What we don't understand is whether life gets started often, given a myriad homes for it to live in. And it's very tempting, and normally a normal version of this talk would end here, I think. But I want to just take 5 more minutes if I can, and people can interrupt if not, because I keep coming back to a conversation with one of the most inspiring people I know, a guy called Steve Squires, who was the principal investigator of Spirit and Opportunity, Mars rovers that spent many years exploring the Martian surface, and which were responsible, along with Steve's team, for establishing that Mars was once a wet world. This is a nice shot of Opportunity as seen from above amongst the landscape of Mars. Here's Steve celebrating landing. And I hope we'll see more shots like this tonight, although I guess socially distanced. I once talked to Steve at the point where they'd established that Mars had had substantial water, but that the liquid on the surface, although it was water, was acidic, about as acidic as sulfuric acid that's used in school chemistry laboratories. And I remember telling Steve I was disappointed because it wasn't Earth-like. And Steve, who was tired and trying to run a Mars mission and had probably been fed up of being asked stupid questions by interviewers, said, look, we don't go to Mars to find Earth. We don't go to Mars because it's Earth-like. We go to Mars because it's Mars-like, because it's different, because it has a different story to tell us than the Earth does. And if we want to understand how these things called planets work, we need as many different stories as possible. So the fact that it's Mars-like, that it's different, is actually inspiring, and we shouldn't be put off. And so when I think about the 4,000, 5,000 planets that we know of, I want to make sure we've captured all their stories, because that's how we'll retell our own. And the story of the history of the solar system is already being rewritten by exoplanets. I've mentioned that we've come to terms with the idea that planet formation is chaotic, that there are these periods where planets can migrate in the system. That's why we have these hot Jupiters that I mentioned. And that statement may bring together many of the mysteries of our solar system. So just in the inner solar system, Mercury is like the core of what was once a much larger body. It's much denser than you'd expect for a planet of its size. Venus rotates really slowly. Its day is longer than its year. And on the moon, there's an image there of, I think it's the Apollo 16 lunar module and the tracks left by the astronauts. The thing that the Apollo missions seem to have taught us is that there was a period early in the solar system's history where something called the late heavy bombardment happened, where an enormous number of impacts hit the inner solar system. So there must have been, for some reason, an enormous flux of asteroids or meteorites through the center of the inner solar system at the same time. And we can explain all three of these things through chaotic planet formation. It's now widely believed by people who simulate these things that we may have formed as many as 30 Mars-sized worlds in the inner solar system. And they would have interacted with each other. So Mercury could be the remnant of a collision, just as the moon probably formed from a collision with the Earth. Venus may have had its rotation slowed after such a collision. You have to think of the inner solar system as a box of marbles being shaken around early on. And the late heavy bombardment may be caused by similar effects in the outer solar system. And so the history of everything we see around us here is being rewritten because we look out at the wider universe. And for the first time, we have new stories of other planets to tell. So I'm going to finish with this shot. This is from NASA's planet hunting Kepler satellite. And this is what happened when the Earth gets in the way of your planet hunting satellite. So this is a detection of a planet, but perhaps it's a planet whose history needs rewriting. So I hope that's fun. Sorry about the technical difficulties, and I'm happy to answer as many questions as we can get in before a robot lands on Mars. Thank you very much.
Thank you, Chris. We'll let you have 10 seconds to breathe and drink some water. We've had some fantastic questions come through, both in the chat and in the Q&A, and some really great feedback from our audience, so that's excellent. So I'm going to choose a few questions to ask, mostly ones that are not too hard and hopefully not too easy, but a good balance. Okay, so my first question comes from Graham. Graham has asked that, or he said, many of the exoplanets you've referred to have orbital periods that are shorter than those in our solar system. Is this because they're easier to see, so that we've discovered them first?
Yes, that's right. So both the methods I talked about are sensitive to planets that are close to their star. In the case of the blip, the transit method, the dips are bigger and they come more often when they're rotation. Actually, the Planet Hunters project that I talked about with the volunteers, we're good at finding planets further from the star because it's harder to do that automatically. But same with the wobble. The wobble is less if your planet is far away. So that's a bias, which we think we understand. And we'll just have to be patient and work hard to slowly fill in the rest of these. There are some interesting ideas about how we might find Jupiter-sized planets in Jupiter-like orbits, which we haven't been able to do yet.
Cool. Okay, this is a great question that I just really liked because I found it interesting. But so Mike asked, why is space so clean? And how is all the gas and dust in planets and stars? So that, it's a really good question. I'm trying to remember, I think the statistics, if you start at the top of the Earth's atmosphere and you hold your hand out and you fly to the edge of the observable universe, which is not something you should try to do, but if you did that, you end up with 2 dust grains or 2 molecules. It's that empty. And partly that's just space is big. Even the Orion Nebula is a pretty good laboratory vacuum. But a more profound answer is that gravity is really rubbish. So gravity is such a weak force that it struggles to bring things together. And so it's very difficult to form a star, and it's difficult to form planets from the rubble. And so in most of the universe, gas will just sit there and mind its own business. It's only when you cool it down and essentially remove any influence other than gravity that any of this interesting stuff can happen. Cool. Okay, so Azumbo has asked, how will the gravitational effects of the proximity of the TRAPPIST-1 planets affect, habituality? That was a hard word to pronounce. On the outer planets.
Yeah, it's a good question, and this is why I tried to get away from just calling it the habitable zone. And it used to be called the Goldilocks zone because it's not too hot and not too cold. But there are all these other effects that matter. If you're a planet very close to your star, you might be the right temperature, but you might keep the same face of the planet facing the star, just as the moon keeps its same face facing us. And that probably creates a very strange environment to live in, if nothing else. It's either day or night and nothing in between, and you'd have strong winds and generally be fairly awful. You can also have stars where the stars are active. So in terms of the interaction between the planets, they do affect each other. We have planets where we see planets arriving late or early for their transits because they're pulled by the other planets, which is fun. It's actually useful when that happens. But I'm not sure that affects the habitability. It affects probably your view as a tourist, and there are probably evenings where you get a much better view of the other 6 planets than others. But I don't think there's a habitable consequence, because I think those things are stable over the long term.
Cool. I just have to say, I think you're really great at answering questions, and I really appreciate that. Okay, so Emily has asked, how do you tell the difference between a solar cycle, so sunspots, and a planet dimming the star?
Yeah, so this is really tough. One of the things we rely on is that, at least for our sun, sunspots don't last very long. So this is why seeing one blip is generally not enough to claim a planet, even though sometimes we see one and we're excited. So if you see something that repeats many times, then it gives you confidence that it's a planet and not a star spot. There are also things like the shape of the dip, like how you go from the maximum down to the minimum. That shape tells you whether it's something that's round getting in the way, or whether it's something on the surface of the star. So there are subtle effects, but it's a difficult thing, and we may be being fooled some of the time. If we only had 3 planets, I'd care about that, because we have 4,000. Even if we're fooled 1% of the time, most of the conclusions that I talked about don't change. And there are a significant number of planets where we have both the dip and the wobble, and those tie together, and then we can be sure.
Okay, so this is more of like a nomenclature. Sorry, Anna, a nomenclature question. So is there a standard naming convention for systems? So you presented a lot of those exoplanet that made no sense at all. So how did these?
Yeah. So the scientific names come from, you name the star, and then planets in order of discovery are B, C, D, E, F, and so on, because the star is A. And so most of those numbers, HD 864, whatever it was, that's the name of a survey in which that star was included. Now, people have started to cheat and rename the stars. So TRAPPIST-1 has some other name as a star, but when it was identified by the TRAPPIST project as having exoplanets, they said, okay, we've got a new stellar catalogue. This is TRAPPIST-1. There is an attempt by the International Astronomical Union to give more poetic traditional names to planets, and there's a large competition run worldwide. But sadly, scientists like me are very boring and don't use those names at the minute, and so we stick to our telephone numbers. It'd be awful if we do discover aliens and have to tell them that they live on HD 8468253C or something.
Or if aliens come here and tell us that we live on a random planet.
Well, that's true, yes. At least Teagarden's star has a name. So that nearby one, we're okay.
Okay, so I have 2 more questions for you. First one just came in from Peter. So do binary stars have planetary systems?
Yeah, great question. Yes, they do. And this is part of our general surprise that planets seem to exist everywhere we can imagine them. So you can have planets around one star of a binary system, but there are also things called circumbinaries, where you have 2 stars in orbit around each other, and then the planet orbits both stars. And then there's one example, which was found by planet hunters, of a 4-star system, 2 pairs of stars in orbit around each other, like this, and then there's a planet going around 2 of the stars. And so understanding how those things form is quite difficult. And I think it tells us that planet formation is easy, and that it happens fast, because you've got to form the planet before the stars disrupt the disk. But there's lots more of work on that to come.
So my final question for this evening, which is going to lead very nicely into tonight's events. Are we going to go to Mars? As humans, are we going to go there?
I think so eventually, and I hope so, because I think there are enough people who want to go. And I think as long as we're prepared to accept some risk, it's about the same risk as climbing Everest in the 1970s, perhaps. I think that's doable. And I think eventually there'll be enough people who want to do that. What we haven't worked out is the finances. How do you pay to go? and things are moving rapidly, as probably people watching know. I do have one hope, though, which is that Mars is the solar system's great wilderness. It's an untouched environment that may have had and may still have life. And I hope that we get to investigate it before we contaminate it. And so my ideal mission would be to nearly go to Mars. I'd love to go to Phobos, the little moon of Mars, set up a station, and from there you have the best view, and you could control in real time, not with the 10-minute delay we're facing tonight, waiting to hear what's happened to Perseverance. You could control in real time what's happening on the surface. We could have the scientific adventure of a lifetime. But I suspect what will actually happen is people want to go and put a flag on the tallest mountain in the solar system, and people want a base to go and visit the Valles Marianas, the canyon system. And I think that will happen within this century. Whether it'll happen in the next 10 years or not, I'm not sure.
How exciting. I'm going to share a link to all of our attendees. There's a YouTube link. Don't click on it before you leave the webinar, though, just to the live broadcast for the Mars landing this evening. So it's nice coincidence that that's happening tonight. And I'd just like to say thank you so much to Chris for joining us this evening. I'd really like to thank Anna as well for interpreting our lecture tonight. At the end of this lecture, when we end it, it's going to be abrupt. So there'll be a survey that pops out. So please tell us what you think of tonight's talk. And also, we'd love for you to join us at our next Institute of Physics Prestige lecture with Professor Helen Gleason. She's going to be talking about liquid crystal elastomers, and it's called A Bit of a Stretch. Helen is a fantastic speaker, so you're really in for a treat. That's on the 16th of March at 7:30. So with that, it is almost 8 o'clock. I will say goodbye to everyone, and also good night, and enjoy the Mars landing. Thank you for joining us, Chris and Anna, and I'll wave goodbye. We could all wave goodbye. Goodbye.